Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on February 27, 2026, about 4 days ago. It introduces a framework called memory caching that allows recurrent neural networks to dynamically expand their memory capacity, effectively bridging the performance gap between efficient recurrent models and powerful transformers. The paper is titled Memory Caching, RNNs with Growing Memory. And as we'll see later, the results are really impressive, showing that these enhanced models can handle long context with significantly better efficiency. To understand how this works, Figure 1 illustrates the overall memory caching method. On the left, notice the cached memories, which are compressed checkpoints of the model's state stored from previous segments. Standard recurrent networks rely only on the online memory shown in the purple box, which limits what they can recall. However, this framework retrieves information from those past checkpoints and combines them during the aggregation phase on the right, using strategies like residual memory or memory soup to maintain long-term context. Well, Figure 2 details the sparse selective caching variant, which specifically targets efficiency. On the left, a router mechanism scans pooled representations of past segments to decide what is relevant for the current context. It then selectively retrieves only specific blocks from the cached memories, rather than processing the entire history for every token. This sparse approach is visualized on the right, where the effective memory shows only certain colored blocks being active for reading, operating similarly to a mixture of experts model to reduce computational costs. So, moving from the design to the evidence, Table 1 reports the performance on language modeling and common sense reasoning tasks. The data is divided into two blocks: smaller models trained on 30 billion tokens at the top, and larger 1.3 billion parameter models trained on 100 billion tokens below. Focusing on the larger models in the bottom section reveals a clear trend. The Titans model enhanced with gated residual memory achieves an average accuracy of over 58%. This significantly outperforms the standard Transformer++ baseline at 53%, demonstrating that memory caching successfully closes the gap with attention-based models. Alright. While the previous results focused on general reasoning, Table 2 stress tests the models with the needle in a haystack benchmark. The columns display accuracy across three tasks: passkey, number, and UUID retrieval at context lengths up to 16,000 tokens. You can see the limitation of standard recurrent models in the deep linear attention rows, where performance crashes to single digits on the hardest task at 16K. However, the Titans model enhanced with gated residual memory completely reverses this trend. It maintains perfect 100% accuracy on passkey retrieval at the longest context, significantly outperforming the Transformer baseline, which falls to about 80%. So, having established that these models are accurate, Figure 4 demonstrates their efficiency by plotting training throughput against context length. The left panel reveals a critical trend. The gray dashed line representing the Transformer starts high but plummets as the context grows to 32,000 tokens, illustrating its computational bottleneck. In contrast, the memory caching variants, shown in red and blue, maintain a nearly flat line. This stability means that, while they might start slightly slower, they become significantly faster and more efficient than Transformers for long context tasks. Wrapping up, the key takeaway here is that we can bridge the gap between fast recurrent networks and powerful transformers. Memory caching proves that simply storing and retrieving past states allows linear models to master long contexts without the exploding computational costs of attention mechanisms. This implies that efficient recurrent architectures are still very much in the game for next-generation language modeling. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.